Let's go ahead and start today's class. I would like to thank Professor Harold Reicher from University of Northern Carolina, I think, a professor of mathematics who shared his notes with us. So most of this material is from his handouts and notes about this idea of the bug crawling. But somehow we can connect the two stories, the bug crawling, to uh, what we did 2 weeks ago. 2 weeks ago, we answered this question: if you have a bug which starts at the origin, and each minute it either moves left or right with equal probability, what is the probability that after 6 moves the bug is back at the starting point? All right, so and the way we looked into that thing eventually was, well, okay, so let me draw the picture. So if you have this bug starting at, this is the starting point, and at each move we can either make one left or one right. So that's minus 2, 2, minus 3, 3, minus 4, 4, minus 5, 5, minus 6, 6. Obviously, we can't go further than 6. So this is our starting point. All right, there you go. We have equal probability to make either a left or a right, 1/2 chance. And ultimately, we decided that pretty much the only squares we can land to are which vertices. Which integers can we hit after 6 moves if we are only allowed to make a left or a right? Yes, that's correct. So we can only hit even numbers, right? So we can either end up in any one of these points. That's it. And then the whole idea is to calculate the number of ways you end up in any one of these, the total number of ways. So the question is asking for a probability. What is the denominator of that probability? The probability that after 6 moves, we are back at the origin. Yes, the denominator would be 2 to the 6. We have 2 choices at each move because we make 6 moves, 2 to the 6 moves. Okay, now the probability distribution will be 6 choose 0 ways because we make 0 right, 6 left, or we can make 1 right, 5 left, or we can have 2 right, 4 left, or we can have 3 right, and then 2 left, 3 left, 4 right, 2 left, 5 right, 1 left, and then 6 right, 0 left. That's it. And the question is asking, yes, 6 choose 3 would be the denominator, the numerator, I should say. That's the desired probability. So this is the probability that after we have 6 moves to go back to this. You can think of this as the following. It's as if I'm pouring water from the top, 1 unit of water, and then it finds its way to the bottom. The question is how much water will accumulate if I go to the 6th layer after 6th move, right? Let me just go ahead and do that. So this is the missing part, right? So if I'm dropping 1 liter of water, so how much will accumulate in each of, and then I put a cup here like that. So this is, oops, sorry for that. So this is minus 6, minus 4, minus 2, 0, 2, 4, 6. So you guys can see that half of the water will spill to this side, half of it will be spilling to this side. Then 1/4 over here, 1/4, 1/4, 1/4. Now we should be careful here. This one is 1/4, and then this 2, 3 here, we go either from here to here, right? So, oh, sorry, this one's 1/8, sorry. 1/8, 1/8, right? This one is a 1/8, 1/8, 1/8, and so on. So you go all the way down, and then you count how many total number of ways to get to the bottom. And this is exactly the count. 6 choose 3 ways to accumulate. So this is the height of the water in this bucket would be 6 choose 3, well, the volume, I should say, 6 choose 3 over 2 to the 6. And then this one will be 6 choose 2 over 2 to the 6. This one is 6 choose 2 over 2 to the 6. 6 choose 1 over 2 to the 6. 6 choose 1 over 2 to the 6. 1 over 2 to the 6. 1 over 2 to the 6. And that's it. All right. Sometimes I feel like you guys are enjoying the chat box more than you enjoy the class. For some of us. All right. Let's keep the chat box public for the time being until yeah. It turns out it is possible to algebraically describe this procedure as well. And so we are making a left turn or a right turn raised to the power 6. And the question is asking you the coefficient of the term L cubed R cubed. Obviously, the coefficient of L cubed R cubed is 6 choose 3. And because each one has a 1/2 chance, so replace L with 1/2, R with 1/2, and boom. So that gives you the exact result that you are seeking, which is 6 choose 3 times 1/2 cubed times 1/2 cubed. So in a sense, this is a binomial event distribution. Do you guys agree? We're in good shape? All right. Write P if you agree. All right. Power down. Wait, you guys can hear me, right? Test. Oh, okay. Sounds good. All right, let's start with one of the interesting problems for today. This is the only 3D shape that we will be working on. All right, so the bug is on a cube. At each minute, the bug crawls to an adjacent vertex, each time with equal likelihood. So we might as well just go ahead and create the cube if you want. All right, there we go. Okay, so I have my cube. All right. So let's assume that the cube starts right at that corner. So the probability that after 8 minutes, we will come back to that corner. I think one of the methods would be just to add some structure to this. Okay, let me go ahead and add some structure. So why don't we think of this as the x-axis? This is the y-axis, and this is the z-axis. And well, and then so the goal is to get back to 0, 0, 0, right? To the point 0, 0, 0 after crawling. Okay, let me give you some time to think about this one, I guess. Oops, sorry. Okay, so can you give me a sequence of moves where we can, for instance, okay, let me give you the sequence. For instance, we can start at this point, and we might, oops, no, not like that, sorry for that. Okay, there you go. That was annoying. Okay, there you go. All right, so I can move like that. I can go up, I don't know, like that, 3, 4, I don't know, 5, 6, 7, and I'm back 8. So I did crawl, and after 8 minutes, I'm back at the at the origin. So in a sense, I need, yeah. So how do I handle these type of problems? So what's, oh, nice. I like it. Yes, recursion definitely works on this one. You can do what's it called? You can establish a bijection if you want to. That's also possible. So let's do both ways, actually. So that was, my first thought was, okay, so here you go. Whenever so suppose that I start at 0, 0, 0, And I'll do the following moves. Let's see if someone can transcribe to me what I'm about to do. I start at 0, 0, 0, and I will end up at 0, 0, 0 with the following moves. X, X, Y, X, Y, X, Z, Z. Can someone explain how in the world does this mean start? So what is the path I'm following here? X, X, Y, X, Y, X, Z, Z. Yes. So, but what do I mean when I write X, X? So where am I going? So I'm at 0, 0. What's the next point that I'm moving to? So whenever I write X, I mean I'm moving along the X direction, orthogonal. So we have three orthogonal directions, X, Y, Z, right? Whenever I say X, I make either one unit right or left, depending on which of where I am, right? So I want to remain inside the cube, all right? So here the first X will move me from 0, 0 to 0, 0, 0 to 1, 0, 0. And then the second X will move me back to the origin. The Y will take me 0, 1, 0. Then the X will take me 1, 1, 0. Then the Y will take me 1, 0, 0. And then the X will take me back to 0, 0, 0. And then Z takes me to 0, 0, 1. And then the Z takes me back to 0, 0, 0. Do you guys see that? All right. Why is this useful then? You guys said it all correct. If you want to start at 0, 0, 0 and end at 0, 0, 0, you want to operate on a direction, on an orthogonal direction, an even number of times. Yes, and that's pretty much it. The rest is just to identify how many ways can we have X, Y, Z an even number of times. So all we need now is to construct the table. Let me go ahead and construct that table. So we have X, Y, Z. There you go. Well, I believe everyone can see what this direction is, or maybe I can put it like that. Okay, good. So let's go ahead. So X, Y, Z can be, well, X can be 0, Y can be 0, Z would be 8. Or X can be 0, Y can be a 2, Z can be a 6. And then 0, 4, 4, 0. Do you guys see that I'm trying to first count all the situations where X is 0. Then I can go to the situations where X is 2. 2, 0, 6, 2, 2, 4, 2, 4, 2, I think. There are so many cases. 2, 6, 0. I think we are done with the 2s, right? Next, 4. Let me go all the way down. Okay, so 4, 0, 4, 4, 2, 2, 4, 4, 0. I think we are done with the 4s. Next, the 6s, 6, 0, 2, 6, 2, 0. And finally, 8, 0, 0. That's it. These are all the all the different ways of ending up at 0, 0, 0. That's it. We call this method bijection. We established a bijection between these XYZs, these sequences of 8 XYZs, which starts at 0 and which starts at the origin and ends back at the origin. So it's pretty good. It's instead of a 3D picture, I now have all these cases. We need to now count every single one of these. And then because the question is a probability question, can someone tell me what is the denominator of the desired probability? I'm kind of scared to look at the chat box. Yes. Do you guys see that? We have 3 choices at each vertex. If you are at a vertex like this, you can go to any other 3 vertices. Yes, 3 to the power 8 would be the denominator. The numerator is really ugly. So you guys, let me write out a few of the first few, and then you guys can calculate the rest of it. Unless someone, well, actually, let's do it as an exercise. Let's see who will be the first to calculate it correctly. So let's keep the denominator like this. So don't simplify. So let's see. Let me just give you the first few so you guys can have an idea. So, oops. There you go. All right, so the first one, 008. So, well, it is just 8 choose 8, right? So 8 choose 0 times 8 choose 0 times 8 choose 8. The next one would be 8 choose 0. That's, oops, oh, shoot. Okay, 8 choose 0, 8 choose 2, and then 6 choose 6. Do you guys agree? The next one, which is, I think I'm overdoing it, right? So this one is 8 choose 0, 8 remaining, 8 choose 4, and then 4 choose 4. Do you guys agree? So here I am asking you, how many different ways can I arrange 4 y's and 4 z's? It's just 8 choose 4, right? That's pretty much. Actually, whenever it's 0, it's easy to do it. So I don't have to write it like that, right? So that's easy. Okay, let's do it again. Okay, so my apologies. So the first one will be only 8 z's. There's only one way to do that. The second one, 2 y's and 6 z's. That's just 8 choose 2 ways. The next one, 4 y's and 4 z's. That's just 8 choose 4 ways. The one after that, 8 choose 6 ways. The one after that, 1 way. The one after that, 8 choose 2 ways. This one is, okay, so this one is, we need 3 of them. 8 choose 2 ways to arrange the x's, 6 left, 6 choose 2 ways to arrange the y's, and then the remaining are the z's, so I don't have to do anything else. The same thing here, 8 choose 2, 6 choose 4. The same thing here, 8 choose 2, 6 choose, oh, well, sorry, this one is still a 0. Okay, good. So just 8 choose 2. This one is 8 choose 4, 8 choose 4, 4 choose 2, and so on. Unless I messed up, 8 choose 4. Like I said, it is, okay, 8 choose 6. All right. Yeah, because the chat box is so crazy, I'm gonna just do a small modification. Sorry, guys. Yeah, so, all right, so let's do the chat just to me, right? All right, so just give me a second. Let me just change the configuration. Yes. Host only. There you go. If I can make it. I think I did. Wait, did I do it? Wait, I failed to do it. Okay, let me try again. Okay, let me try one more time. Ah. Please disable. Okay, I think I did it. Yes. Okay, perfect. Now I can see your answers. Otherwise, it's so confusing. Okay, so did anyone add up all these cases? Yeah, I know it's torture. All right, let me do it for you. If you add up all the cases, I think this comes out as, and please do it later on when you have time. This comes out as 1,641. That's it. That's the desired probability. 3 to the 8 was, okay, let me check my calculator. 3 square, 6,561. So the answer is, well, obviously you can simplify it, but I won't. 6,400, wait, what did I say? 6,561. All right, so that's the desired probability. Now another question. What is the probability? Yes, very close to 1/4. What is the probability we will end up after 6 moves, we will end up at a point like this? What is the probability of ending up at a point like this? 0, 1, 0. After 6 moves, what is the probability I will end up at that corner? That's right. There's no chance I can end up there, right? Because after 6 moves, if you check the coordinates here, so this is 0, 1, 0, which add up to an odd number, but my number of moves are even, right? There's no way I can end up at that corner or that corner or that corner. All of these three are all 3, 0. However, let me change the question. What is the probability I will end up at this corner? 1, 1, 0. This one is definitely possible. Nice. Who can guess what is the probability here? The probability I will end up here after 6 moves. We already know the probability after 6 moves of ending up at the starting point. Ah, so really, really nice. Okay, so we have some smart, cool people in the classroom. No, it's not the same probability. It's a different probability. But I think, yes, I think a lot of you guys have seen it. Okay, so you guys can guess it. So the probability, we will go back to the start, is this probability. We can call it P0, for instance. And like you guys, some of you guys mentioned it. Yes, because ending up in any of these 3 points, this, or this, are equal probabilities. Let's call it P1, P2, and P3. They are all equal to each other, right? P1 is, because of symmetry, P3, and that probability better be 1 minus whatever that P0 was, all divided by 3. That's it. And interestingly, if you make the calculation, because you guys already suggested it's very close to 1/4, indeed it is. The others are 1640 different ways to come back to those, one of those square points out of 6,561, if my calculations are correct. Why is 422 case? Okay, let me check. I think there's an error in the 422 case. Let me check. Someone is asking me. So the, oh gosh. All right. Yeah, my computer is pretty slow, actually. Sorry for that. All right. Okay, so for the 422 case, okay, there you go. So I think the question is 422, this one. Oh, yeah, that's a mistake. Yeah, sorry for that. Yes, that's definitely wrong. There's 4 left, 4 choose 2. Yes. Good. Or you can use Mississippi, right? So here, 422 case, you can do it as 8 factorial over 4 factorial, 2 factorial, 2 factorial. Do you guys agree that these are the same thing? So you can either write it like that, or you can write it like Mississippi. It's the same thing. Awesome. So let's move on, people. Oh, no, let's not move on. You guys suggested we could have solved this problem using recursion. Let's use recursion to solve the same problem. Okay, let me quickly draw the square again. It turns out recursion is pretty cool. Okay, so da-da-dat, da-da-dat, da-da-dat. All right, so we start at that corner, and the question is asking to go back to that corner. Let me draw the coordinates. So we are here, or there, or there. The bug crawls along the edges as usual. So from 0, 0, 0, you can go to any of the neighboring 3 vertices and so on. Well, yeah, so what would be the recursion? Well, I think we already agreed that the only points that you can end up are the following points. So you can, so if this is the origin, the point 0, we decided that there is no way we can end up in any of these 3. So this one is ruled out, this one is ruled out, this one is ruled out. The only other points that you can end up are these points, A, B, and C. That's pretty much it. And like we said, because it's an even number of times, everything should be, the recursion should be based on an even number of times. After an even number of steps, we will end up at A, B, C, or the point O. And okay, so let's write out the first initial cases. So O, actually, let me write it on this side. O2. How many different ways, if you start at O, after 2 moves, you can end up back at O? Why don't you do face reveal during lesson? Well, if I do face reveal for 300 people, everybody will be just staring at the faces rather than the math. 3 ways. Yes, that's correct. 3 ways. Do you guys agree? Yes. You can go from O to that guy and then come back, or that guy and come back, or this guy. After 2 moves, there's 3 ways. You can start at O and then come back to O. How about if you start at A, after 2 moves, sorry, you start at O and after 2 moves you are at A. Sorry, that's the meaning of this. Sorry for that. Whenever I write O to N, what I mean is start at O and end at O after 2N moves. And similarly, whenever I say A to N, so that would be A to N means start at O and end at A after 2N moves. Yes, if you start at O, and so you can either go like this, or you can go like that. There's really 2 ways, which is the same thing for B2 and C2 due to symmetry. Do you guys agree? So for instance, A2 would be, B2 would be, you can follow the pink, either go like that. After 2 moves, there's 2 ways, starting at the origin to end up at B. Okay, so that's pretty good. So we have the initial few conditions. At that point, here's a couple of things. Either you can construct the recursion right away, or if you are not very good with recursions, so you can find the pattern. For instance, you can go ahead and calculate A04 and then try to calculate A4. You don't need B4 and C4 because it's symmetry, right? So, and then so on. You keep going, O6 and A6 and so on. Eventually, ultimately, you can conjecture, you can make a claim about a closed form formula for O4, for instance. So that's one way to finish the problem. Make a guess or conjecture, a claim for the general form, and then use induction to prove it. All right. I'm not going to do it that way, or maybe I should do it that way. I don't know, whichever way. Or let me just construct the recursion directly. So O2n, or maybe I should call it O2n plus 2. If you want to end up at O after 2n plus 2 moves, where were you after the two moves before? If you want to end up at O after 2n plus 2 moves, where were you 2 moves before, after 2n moves? Yes, you were either at O or A or B or C, right? Suppose you were at O. How many ways, if you were at O after 2n moves, how many ways can you end up back at O after 2n plus 2 moves? Yes, we just did it a few minutes ago. 3 ways, right? 3 times O2n. Or previously you were at A2n. How many ways can you end back if 2n moves it later you are at A? After 2n, like after 2 more moves, how many ways? Yes, 2 ways. Okay, so you guys see what I'm trying to say. Yes. And then the same thing for Bn. Wait, is it 2 or 3? Oh, 2. 2b2n and then 2c2n. Do you guys agree? But earlier we established that A2n, B2n, and C2n, they are symmetric. So therefore, really the recursion is this. O2n plus 2 is really 3O2n plus 6A2n. Let me just use A. Why don't you guys try to construct the recursion for A2n plus 2 in terms of O2n? So I'm missing a coefficient here. And in terms of A2n. Does everyone agree how we constructed this one? So basically, we just check if after 2n moves you were at O, how many different ways after 2n plus 2 moves to end up at O? Again, 3 ways. If after 2n moves you were at A, then 2 times that, that's the number of ways to end up at O after 2 more moves. All right, so let's see if you guys can guess these 2 coefficients here. So you want to end up after 2n plus 2 moves at A. So either 2 moves ago you were at O, or 2 moves ago you were at B or C, right? So all you need is, yeah. If you were at O, I think it's yes. If you were at O previously, how many ways can you end up at A? 2 ways. So this one is clear. This one, the coefficient is a 2. So if previously you were at A, next move, like 2 moves later, if you want to go back to A, there are how many ways to do that? If two moves ago you were at A, 2 moves later you can go back to A in 3 ways, yes. If you were 2 moves ago, if you were at B, how many different ways can you end up at A 2 moves later? If 2 moves ago you were at A, 2 moves later, how many? Yes, 2 ways, and then 2 ways from C. So it's really 2 plus 2 plus 3, 7. Do you guys see that? It's slightly tricky. That's it. That's the same. So you have a system of recursions, and technically there's a way to solve this system of recursions. But like I said, this is a little bit more advanced recursion, which this class, the purpose of this class is not that. I know that some of you guys already guessed the form. I think you already did these numbers. So what do you guys get for O4 and A4? We can actually easily calculate them from these recursions, right? And then let's see if we can guess a form. So what is O4? O4, just plug in n equals 1. So it's just 3O2, which is 3 times 3, that's a 9. 3 times 3 plus, I'm just using the recursion, 6 times A2, which is 6 times 2. And that ends up being, what is this? Let's just do the recursion for O4, hold on. This is 9 plus 12, that's 21. Okay, let's calculate A6 now. It's always 3 times the previous O, which is 21, and then 6 times the previous A, which is, oh shoot, I need A4. all right. So I need A4 before I can do A06. Oh shoot. Okay. A4 is, okay, let's quickly do A4. 2 times 3 plus 7 times 2. That's 14, that's a 20. Okay, let's do the A6, O6 and A6. O6 would be 3 times O4, which is 21, plus, oh boy, 6 times A4, which is 20. So what is this? Oh boy, that's huge. 120, 183, thank you. All right, so what's next? A6, can you guys calculate A6 for me? 2 times 21, oh boy, no, oh yes, 2 times 21 plus 7 times 20, is it so? 182. Hey, you guys know it. So basically they are very close to each other each time, right? Because this is also B6 and C6. So these numbers will end up being extremely close, very close to 1/4 of 3 to the power 4, right? Because we have 3 directions we can go to. So 3 to the 4 is 81. Oh, sorry. 3 to the, wait, 3 to the 6. 3 to the 4 is this one, sorry. 3 to the 4 is 81. So one of them is 21, and then we have 3 20s. Do you guys see that? Huh? So I no longer need the, well, oh shoot. Okay, so let's keep the picture. Well, will I need the picture? Okay, maybe I will. Okay, so what I'm saying is 3 to the 4 ways is equal to 21, which is 04, plus 3 times A4, 3 times 20. That makes sense. 3 to the 6, which is 81 times 9, 729, I guess. 183 plus 3 times 182. Do you guys see that? So therefore, yes, it is easy to conjecture rather than trying to solve it closed form like this, which is, I don't know. I mean, it is possible, obviously. I mean, it's not that bad, actually. It's possible to directly make a conjecture about O2n and A2n, which is the same thing as B2n and C2n. So for O2n, I know you guys already did the conjecture. O2n is the larger one, right? So the larger of the two. So it will end up being 3 to the 2n plus 3 all divided by 4. And then the other one would be 3 to the 2n minus 1 divided by 4. Why is it 7A2n and not 6 O2n? Okay. Okay, so yes, so there's a couple of questions about one of the equation. Okay, wow, so a lot of people are raising hands. Yeah, my machine is so slow, I don't think I can, oh, well, okay, so the question is, I think, where did these numbers come from? The 2 and the 7. So the 7 comes from the following. So pretend that at the end of the 4th move, you were here. So the question, sorry, you want to calculate how many different ways after 6 moves you can end up here. Well, what I can do is I can check where I was at the end of move 4. So at the end of move 4, either I was at B or C or O or A, right? So therefore, 2 moves later, how many different ways I can end up back at A? That's the question. If you were at the end of move 4, if you were at O, there's really 2 ways. You can either take this route or this route. So that's why we multiplied it by 2. For the 7, it came from the following. If at the end of move 4, we were at A, if we want to end up at A after the 6th move, we have 3 ways. We can either go like this, go and come back, or go and come back, or go and come back. It has 3 neighbors, 3 ways. Plus, if you were at C at the end of move 4, then what you can do is, let me use a different color, maybe red. Okay, so you can either take it like that or take it like that, 2 moves, and the same thing for B, 1, 2. So if you add these up, that will give you the 7 you want. All right, so this would be recursively solving this, but that's pretty much it. That's the closed form formula, and you can test it. It will give you exactly the same answer as this one, which is 1641 and then 1640. All right, and the denominator will still be the same. All right, let's see if there's any questions so far. 2 plus 2 plus 3 is 7, yes. All right, so we exploded the cube. All right, we can do pretty much, we can crawl the bug anywhere we want, right? So here is a bug crawling. After 7 moves, the bug will have visited every vertex exactly once. I think this one was an AMC question. I don't know if you guys remember this question. Yes, you can do the tetrahedron. There's a lot of different configurations. You can let the bug walk along the edges. I think the tetrahedron was in the AIME a couple of years ago. So the question says, so we start here again at the far vertex. After 7 moves, you want the bug to visit everywhere. So why don't we just label each of these vertices? Oh, sorry, let me be organized. So let E be here, F, G, H. The question is, yes, 7 moves later, obviously you have the potential to visit every vertex. If you don't visit the same vertex twice, then you are in good shape. How many ways can that happen? And then the denominator is easy, right? So the desired probability is, because at each vertex you have 3 choices. What's the denominator? 3 to the power. Yes, because we are making 7 moves, 3 to the power 7. That's correct. All right, so the numerator now, there's not too many ways actually. Okay, let's start. So if you start at A, you have 3 choices, right? So we can start with 3 times. Without loss of generality, we can go to B. Once you are at B, because our goal is to never go back to a vertex we visited earlier. Why? Because there's 8 vertices that we need to visit, and we barely have 7 moves. So we want to make sure no other vertex will be visited again. And in the case of B, B cannot go back to A, so it has only 2 choices. You guys see that? Without loss of generality, let's assume that B goes to C, but there's a 2 times. All right. Now C has really 2 choices. You guys see that? From here, a casework will begin, right? The numerator is not 24. Nope. All right, so let's do the casework. So what are can you guys give me the sequence? So we started ABC. What will be the remaining moves that I should take? 1, 2, 3, 4, 5. All right, give me the sequence. Or 1 acceptable. There's not too many. So if you start ABC, there's only so few. Okay, so yes. Yes, okay, awesome. So one way would be D, go to D, then H, then to G, F, E. That's one way to accomplish the task. Another one would be exactly, so you start with ABC again, you go to D again. That was one of the cases, right? Going to D is one case, and then going to G is the other case. So this is a casework we said, right? Okay, after D, you go to H, but instead of going clockwise, you go counterclockwise, E, F, G. There you go, on the top layer. Or you can directly go up to G, after which there's really not too many choices you can do. Okay, A, B, C, G. Okay, let me again try to highlight it with red. Okay, so we started at A, we went to B, C, G. At G, we have to make a choice. Should we make a left turn or a right turn? Yes, we have to make a left turn, because if we were to make a right turn, then suddenly when we are at H, if we decide to capture D first, then we are stuck at D because all of its 3 neighbors are already taken. If we decide to go to E, F, again, we are stuck. We can never reach D. So really the correct choice at G, once you are at G, is to make a left turn to F, E, H, and D. So there's 2 ways in this case and 1 way in that case, 1 way. And that's pretty much it. You can't go across the cube like through the dimension. Yes. So that the numerator would be 3 times 2 times 3 as a result, which is 9, 18. 18 over 3 to the 7. We can simplify by 2 3s. So 2 over 3 to the 5, I think. Yes. Thank you, guys. Okay, so this was a contest problem. By the way, this is not even the main problem I will attempt today. Today we have a fantastic problem. A bug in the plane moves from one lattice point to another. At each step, 1 unit up or 1 unit down, left, right. Okay, the standard rule. How many different points can the final point be? Yeah, that looks like an AMC8 question, right? Oops. All right, so my computer is stuck again. Sorry for that. I think it's about the software I'm using, so I should change my software. All right, in the meantime, you guys are trying to check that. Oh, come on. This class is supposed to end at 3 p.m., sir. Oh, come on. Well, I'm stuck with that weird screen, guys. All right, no, still stuck. Okay, so anyone did the calculation? Oh, thanks God. I'm back to normal. Ah! Okay, thanks God. Now I'm back to normal. Yes, I think there's in total 121 of these. Yes, definitely. Yeah, so actually, I'll do something here. Okay, there you go. So yeah, 121. Why? Because, all right, so I'm back to my screen now. Thanks God. So we are taking a 10-step move. So in 10 steps, okay, so let's take this a little bit down. All right, the farthest north we can go is 0, 10. The farthest east we can go is 10, 0. The farthest south is 0, minus 10. Or the farthest one here is minus 10, 0. So as a result, technically, we can end up anywhere along this square, any lattice point along this square, which if you count carefully, how many points are there here? How many lattice points? So for instance, 1, 9 would be one of them. 2, 8 would be another one, and so on. There will be exactly 40. Why? Because if you cut them carefully like that, there's exactly 10 here. There's exactly another 10 here. 10 here, excluding that vertex.
What time is your class end?
At 3 p.m.
Cool.
Oh, thank you. All right, so in total 40. Or we can... Oh, it's 2:15. 2:15. Go. All right.
2:16.
Okay, 2:16. 2:16. Go. All right. So an alternative would be we can end up at 8, or this 8, or there over here. What's going on? My son just visited, said hello. Do you guys agree? So we can end up at any point on that one where this is 8, 8, minus 8, minus 8. Do you guys agree? Because it has to be an even number of steps, we have to end up somewhere along that line, right? So let me just get rid of that red line, which is super annoying. Okay, do you guys agree? Or we can end up anywhere on the 666 diamond shape, or we can end up anywhere on the 4 size diamond shape, or finally we can end up anywhere on the 2 by 2 by 2, or we can go back to the center. Don't forget the center, right? How many different points? Well, 40 on that one. Okay, so we just wrote that one. So there's 40 ways. This one is 8 times 4, right? So this one was 4 times 10. This one is 4 times 8, which is 32. This one is 4 times 6, which is 24. 4 times 4, 16. 4 times 2, that's an 8. And finally, one way we can end up at the center. If you add up all these numbers, hopefully, unless I messed up, yeah, it seems correct, right? So we have 40, 80, another 41, 21, 21. Yes, that works. All right, so everybody is happy. I hope that's clear. We can never end up at a point between them. For instance, there are a lot of lattice points between them, but you can end up in those lattice points if there's an odd number of moves. Here we are told there's an even number of moves. Is it a coincidence that it's 11 square, or is it providence? I'll call it providence. I'm sure there's a pattern that we missed. All right, so another question here. I think this was also a contest problem. Let me give you a minute to read the question. Again, you have the coordinate axis. The probability that the token ends at a point somewhere on that graph after how many moves? After 6 moves, yes. After 6 moves. Why is it 121? Because we just added all the potentials. Because remember, in the previous question, oh, I'm sorry, I just need to show you something quickly. We can end up at a point, let's say, like 4, 4, for instance. How can we end up at a point like 4, 4? Well, you can make a sequence of, I don't know, maybe we can do, well, obviously we need 4 right, and then 4 up. Wait, that's 2, 2, right? The point that I marked is 2, 2. So somewhere here, sorry. 4, 4. So 4 right, sorry, 4 left. I don't know the difference between left and right. Okay, 4 left, 4 up. I need 2 extra moves. So I need to waste 2 moves. I can waste, let's say, right, left, for instance. Or I can waste it as an up, down. If you decide to waste it as an up, down, then it would be up to the power 5 and then a down. This is one way to end up at 4, 4, for instance. Oh, shoot, did I mark? No, this one is 4, 4, right? Because it's alongside that thing, which is 8, yeah. No, I don't think I marked 8, 8. Here, this line is the line where x plus y is equal to 8, right? Okay, awesome, awesome. So let's move to this question now. After 6 moves, what's the probability that we will end up somewhere along this line? Or somewhere along this line? Aha, do you guys agree? So the upper one is y equals absolute value of x. The bottom is y equals minus absolute value of x, or you can say, so when I say the bottom, I mean this one, right? This, that. So that's the minus of it. So therefore you get the whole thing. So all the lattice points after 6 moves that we can end up at are pretty much which ones? So we can either end up at 0, 0 or 1, 1, 2, 2. Wait, we have 6 moves, right? 3, 3, and so on. This one, those 3, minus 1, minus 1, minus 2, minus 2, minus 3, minus 3, or 1, minus 1, 1, minus 2, 2, minus 3, 3. That's it. But because there are equal probabilities in play, why don't we just calculate the probability of each of these and multiply them by what? Yes, we can simply multiply each of these by 4 because whatever is the number of ways to end up here, it's the same with ending up here or here or here. There's a cycle there. And then the number of ways to end up in that one of these 4 and so on. However, don't forget, it would be terrible. Yes, don't forget the origin. So the answer, so the question is asking for a probability, obviously. Yeah, so the denominator would be what? We have 4 choices at each thing. So 4 to the power 6. For the numerator, we will end up whatever is the origin, a number, plus 4 times another number. Do you guys agree? This is a bad idea. All right, so I think the rest you guys can make the calculations on your own, I guess. I think it's, I did it, it works. I mean, so for instance, if you want to calculate 3, 3, let's calculate 3, 3. How many ways can we end up at 3, 3? The point 3, 3. One way? No. If you, this would be the question where, do you remember the grid? You start at 0, 0. You end up at 3, 3. How many ways can you do that? We learned it a long time ago. I think you guys should have learned it. Yes, 6 just 3 ways. That's correct. How about 2, 2? Now, 2, 2 is a little bit more casework. So you can end up in 2, 2 in 2 different ways. You can end up in 2, 2. Well, obviously, first of all, you have to make sure you have 2 right and 2 up. And then next to it, you can either add a right up, or you can add an, right left, I should say, or you can add an up down, right? So therefore, the 2 cases for 2, 2 would be r cubed u square L, the first case, or the second case, r square u square, r square u cubed d. Well, the first one, well, both of them, you can either use 6, okay, let's just do it quick, 6 factorial, 3 factorial, 2 factorial, 1 factorial, and this one the same, 6 factorial, 3 factorial, 2 factorial, 1 factorial. And we are done with 2, 2 as well. But don't forget the times 4. The 1 is even worse. The case with 1 is, okay, so I'll leave it to you to figure that one. If you do everything correctly, the answer comes out as what? I think this one comes out as 440. This number over here comes out as 440. This number comes out
24 plus 14.
24 plus 14 is 38. Go. All right. So as a result, the desired probability comes out as what does it come out? 2160. Yeah, 2160 divided by 4 to the 6. Yeah, something like that. But obviously you will simplify by 4. The final answer is 135 over 256. Yes, 135256. All right, and I think this was an AIME question somehow. I remember, well, I kind of feel like it was AIME, but I might be wrong. All right, that's it. Let's move on. Okay, oh, thanks God. Eventually, we came to today's main question, all right? This question, you can have so many different ways. You can change it. You can make it extremely simple, very hard. So first, let's make sure everybody understand the thing. A bug crawls around the plane at a uniform rate, 1 unit per minute. He starts at the origin, at this point here, 0, 0. And then he goes to 1, 1. We go like that at time 1. At time 2, we go up. And then at time 3, we are here. At time 4, we are there. Do you guys see that? Yeah, another bug. So then we can construct this function. And that's the whole trick, is to construct a function depending on time. T represents time. Whenever I say G0, G0 is 0, 0. So therefore, this function takes the values from non-negative integers and maps them to the Cartesian plane. Do you guys see that? Everywhere on the plane. So we are trying to cover the whole plane by just crawling the bug across the lattice points of the plane, but we want to make sure we cover everything. Okay, so here is the picture. So time 5, I'm here, 6, 7. So we do a spiral basically. You guys agree? 11, 12, 13, 14, 15, 16, and so on, 17, 18, 19, 20, 21, 22, 23, 24, 25, 6, 7, 8, 9, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49. So you guys can see the turns, right? So for instance, this is a turning point where I need to start going up. Can you tell me what is the turning point over there on the top, over here? What number? I don't want to keep writing all the numbers, obviously, right? Unless you want me dead. Yes, that would be a 56. What's the next corner that I will hit over here? 64. What's the one down there? Diagonal, like this is a diagonal here, right? This one is a main diagonal. This one is a main diagonal, it seems. Huh? This one is not a main diagonal. These two are not, yes, I think is it correct? Is it 72 or 73? I think it's 72. Let me see, 65, 66, 67, 68, 69, 70, 71, 72, yes. So we go from 56 to 64, 64 to 72, 72 to, tell me one more number here in that corner. 81. How about the one above this one and that corner when we make a turn? We are trying to figure out when do we make the turns, right? At least this will simplify our life. All right, so people say it is 90. I would like to agree with that. And then from 90, where do we go to? 100. Well, from 100 down there, I have no clue about this corner, but okay, I'm just believing what you guys said. How about this corner? This corner, I know what it is, right? Yes, this one, wait, what's the pattern? 121 here, yes. Wow, we are humans. We are pattern-seeking creatures. Don't listen to biologists, listen to mathematicians. We are pattern-seeking creatures. That's exactly. So does everyone agree on why G16 is minus 2, 2? Because after 16 steps, of course, I am at the point minus 2, 2. Do you guys see? 1, 2, 1, 1. right? So the 16 is minus 2, 2. So from now on, whenever I say, what is G, let's say 64, what will you tell me? G64. The coordinate, give me the coordinate of G64. Yes, minus 4, 4. Yes, that's right. That sounds right. I think everybody agrees. Okay, are you guys ready? Are you feeling confident? I highly recommend you draw this picture right now, because for the rest of the class, we will be exploiting this picture significantly. By no means this is an easy picture. All right, so here we go. Do you guys want to, we will figure things out along the way. Okay, the first question shows up. First question, where is the bug after 2008 minutes? Go. Let's see who will be the first one to answer this question. I want to figure where the bug is at time 2008. And then I want to also figure how many turns it did until that time. So you need to give me the coordinates. So the first question is asking G of 2008. This problem is probably from 2008. I don't know. I received these problems from Harold Reicher. I said it at the beginning, from University of North Carolina. So it might be from NHMMT, I don't know. Some of the problems I realized they are from AMC, and some of them are from the AIME. Miss Nal had another handout. She was supposed to make this class. She has an extensive handout about bug crawling. I never looked at these problems that much, but apparently this is a very favorite topic in the med counts on AMC10 and on the AIME as well. All right, so we need to answer two questions here. Where is the bug after 2008 minutes? And how many crawls did it do until then? Okay, so so far we had a couple of guesses. None of them are correct. Oh, wow, we have one correct. All right, so far we have at least one person who got it. Aaron has it. All right, so one. Let's wait until at least 3 or 4 people gets it right. Okay, Ryan got it too. So far we have 2. You make sure the X and Y coordinates are organized in a correct way. Some of you guys, you are the wrong direction. All right, Lurchin. Yeah, Lurchin got it. Yay. This is an annoying problem, right? So you need to figure out the pattern in this picture. Very important. The reason I like this picture a lot is that it's showing you a one-to-one onto function, which maps the whole thing. Andrew got it as well. Thank you, Andrew. Emma, just flip the axis and the X and Y axis, and then you will have it right. Yeah, Steve got it as well. Thank you. Victor is very close, but not quite there. No, Kartik, try again. Emma got it as well. Matthew, have it. Oh, wow. Okay, so most of you guys already figured, I think, a couple of things that can help us. The number 2008, what do you investigate about the number 2008? What about 2008? So where do we start this question? 2008, I'm investigating. Yes. Okay, good. I'm investigating the squares, the perfect squares before and after it. Why would I do such a thing? Which guy would do that? Which girl or guy would do that, right? So it's between 44 square and 45 square. And I do it for the following reason. We saw a pattern a few minutes ago. This was the main diagonal. On the y equals minus x line, this is where the even squares lie, and it's kind of off by 1. This is not the same diagonal. Off by 1, this is where the odd squares lie. Do you guys agree? So wow, but the two diagonals are not the same. This one, the first line that I draw was y equals minus x. The other one is y equals minus x plus 1. So this one is the diagonal y equals minus x plus 1. It is just shifted up by 1, right? This one is this yellow diagonal is y equals x. All right, and that's pretty much it. So noticing that 44 square will end up somewhere on that top diagonal, somewhere up there. So all I will do is I will crawl down that diagonal by how many units? By 44 units. And then I will crawl to the right by that whatever many units it is, right? Wait, no, that's not true. Forget about what I just said. Wait, was what I said was true? So let's think about it. So 44 square is somewhere along that corner, 44 square. And let me close the window, hold on. All right, there you go, 44 square is there. And then we scroll down all the way until we reach that other corner. If you check the pattern, it was like here, the pattern was like we crawled like 10 units. Here we crawled 8 units until we reached the bottom left corner, right? So therefore, this corner here is 44 square plus 44. But 44 square is 1936. If I add 44 to it, it will give me 1980. I'm still short of 28. So I need to go this direction by 28. And boom. So then I will end up at whatever. Now the rest is just to identify the place. Okay, just let's continue the pattern. 100 is in which vertex? It's in the okay, so for instance, this one is the point 2, minus 1, 1. This one is minus 2, 2. This one is minus 3, 3. This one is minus 4, 4. This one is minus 5, 5. Do you guys see? So this is 10 square. It's as if I'm splitting 10 into 2 parts. So therefore, 44 square is at the point minus 22, 22. All right? Oh, by the way, for those of you who already finished and you want to see the next question, that's the next question. How many minutes does it take for the bug to get to the ordered pair, this one, 1999? All right? How many minutes until you reach? So this time, in the previous question, we are given the minutes and it's asking the coordinates. Now we are given the coordinates and it's asking us how much time until we get to that lattice point. All right. Okay. Question. Wait, we didn't do the turn. What? Question yet? Oh yeah. No. I'm going back to A. I'm just showing the question B. If you are bored, if you already know how to solve A, you don't have to listen to me. So just tell me how many minutes until we reach to 1999. All right, where was I? Oh, okay, so 44 squared, we go down by 44. So 44 squared is at this point. If we go down by 44, then this vertex is minus 22, 20. Sorry, minus 22, minus 22. And then because we need to go 28 in that direction, that will give us minus 22 plus 28, so minus 6, minus 22. So that's where we are after 2008 moves. All right, so the next question says, how many minutes until... Okay, so let me check the answer. Hold on. The answer is... Okay, can you rewrite what you guys said? Okay, Shai Hua already have the answer. Kartik is very close this time, but still not quite there yet. Nope. So far, at least one person got it. So the answer for the part A was minus 6, minus 22. So at home... Yes, Henry got it as well. So far we have 2 people who got the answer. Oh no. Okay, make sure you understand these diagonal patterns and especially how... Yeah. Nice. Okay, actually, you know what? Some people are saying there was another way we could have found that minus 6, minus 22. We could have gone backwards. Yes, that's right. Some people don't have the money to buy pencils. Okay, Ryan have it. Kartik have it now. Thank you, Kartik. Hacker has a lot of... None of them correct, Hacker. Andrew, correct. Yes. Okay, I think people already have a guess. Okay, so let me, we know exactly the minus 99, right? It has to be before that point. Do you guys agree? So minus 99 is exactly where after t is equal to 198 square, based on the pattern that we just found. Remember, anytime it is 10 square, you are at the point minus 5, 5. So if you are at, after time 198 square, so wait. Yes, we are at the point minus 99, 99, which means, but because we are before that point, we need to go rightwards, backwards. So do you guys agree? So we are at that corner minus 99, 99, and we want to go backwards along that top row, the y, along that same row, yes. So therefore, we want to go backwards how many units? We want to go 99 plus 19, 100 and, well, okay, so basically we want to subtract from it 99 and then 18. Do you guys agree? So that many before. So that would be the answer, I think, unless I messed up. An alternative way would be the following. Oh, it's 19, sorry. 19, thank you. All right, an alternative way, yeah, therefore the answer is 39,086. All right, an alternative way is to figure out what is the other diagonals. For instance, can someone tell me the pattern for this diagonal? Can you guys see the pattern? So what is the pattern for these numbers? 2, 12, 30, 56, 90. Ah, Justin, have it. Fy greater, have it. Fy greater, have it in another way. Yes, Forrest and yeah, so exactly. So 2 is just 1 times 2. 12 is 3 times 4. 30 is 5 times 6. 56 is 7 times 8. 90 is 9 times 10, and so on. So therefore, that corner up there on the right, upright corner, that corner would end up being 197 times 198. And then you need to go leftward. So you need to add a few additional steps. I think 80 more steps. So that's another way to find that number. 197 times 198 plus 80. All right, either way works. They are both giving the same answer. Okay, how about this question, part C? This is a weird question. So you want to, after t units, after time t, you are at this coordinate point. After t plus 23, 23 minutes later, you are at that point, and you want these to be 17 units apart. When I say 17 units apart, I don't mean the taxi cab distance. I mean the Euclidean distance. How in the world can two lattice points be 17 units apart? How? Like, I thought it was supposed to be like, why is it not 23 units, right? Yes, we need a right triangle, a Pythagorean right triangle where the hypotenuse is 17. And we already know one, which is 8 and 15. And surely they add up to 23. It makes perfect sense. Now tell me which one is the smallest one, the smallest time. What is the first time t? If I add 23 to it, we have that distance. Basically, give me those two times. Give me the time minus another time where their distance, d, from now on I will show distance like that. Their distance is, so give me two numbers, t and t plus 23. No, 8 is too small. Remember, you want to go all the way to 15. One of the side lengths would be 15, right? So you need to go quite a bit. Yes, Kartik has it. Good job, Kartik. Oh, wait. Kartik, you are one off, I think. Oh, no, you're not. Wait, are you? I'm not sure. Yes, this is a tricky question. Yeah, you might think that, yes, I think, Kartik, your solution is slightly wrong. Yes, 210, 233 is not the first occasion. It happens before that. Before 210, 233. Yeah. Okay, so this question is kind of a little bit annoying. But 210, okay, so, all right, so, wow, I have no space left. But if you check G210, where are we in time G210? Okay, this is, so you just check the corner points, and I think G210, we are at the point -7, -7, all right? So at G210, we are at -7, -7. If you check G225, we are at, 8 - 7. So forget about the distance. Yes, okay, some of you guys got it. Yes, the one which works actually is G202. Yes, so if you check G202, okay, so let me write that down. G202, at time 202, the bug is exactly at -7.1. And sure enough, after 23 minutes, it ends up at, I think, if I'm not mistaken, it will go to 8 minus 7, so 225, yes. 225, oh yeah, we have it, that one here. So basically this one, okay, let me write it next to each other. 202, we are at -7.1, and sure enough, in the Cartesian plane, these two lattice points, they are, so their distance between them is exactly 17 apart. Yeah, so, but guess what? These are easy peanut questions. We can make significantly harder problems out of this deal. Ultimately, there are some open-ended questions related to this bug crawling thing. So you might wonder, right, why do they ask AMC10 kids like AIME, why do they keep asking those bug questions, right? So you might feel like these are very important questions, right? And we will see it next. Okay, so here is our next question. This one is slightly open-end. GT is, okay, so let me redefine GT, some of you, okay, so GT is you tell me the time, and I tell you exactly where the bug is at that time. So for instance, G0 is 0, 0, because the bug starts at 0, 0. G1, at time 1, the bug is at 1, 0, I think, right? And then at time 2, the bug is at 1, 1, and so on. Remember how we create this spiral? And this way we are able to hit all the integer coordinate points, so which is pretty good. Okay, the question says, suppose that one bug lives 99 minutes after the other one. So basically what we want is these two bugs, what is the closest that they can get? So 2 points, which are 99 away from each other along the line, along that thing, but they are closest to each other. Nice. Hacker has an idea. Now, Hacker, you have a huge claim. Now you need to prove your claim. What do you guys think Hacker guessed? Yes, Michelle, that's correct. That's what he guessed. Now I'm challenging him to prove his claim. Okay, guys, Hacker thinks that these two bugs, obviously that distance cannot be 0, right? 0 means they are at the same point. There's no way they can be at the same point. One might wonder, what is the smallest? What is the next smallest? It is 1. Yes, it is possible that two bugs, they are just 1 unit apart from each other somehow. But the question is, at which minute? At which minute will they be, or at which location? Give me the location or the minute, doesn't matter. All right, so we need to go back to the previous picture, or maybe I can redraw the picture. Okay, so let me redraw that picture over here. We need to further exploit this picture, right? So let me give you a few minutes to think about this. We really need to find some good patterns here. 10, 11, 12, 13, 14, 15, 16. I won't bother writing it. It's better just to draw the lines and just to label the vertices, right? So that's way easier. Because the critical thing is the vertices. Once you have the vertices, the rest is very straightforward. You just go left or right or up and so on, right? Okay, something like that. We keep going this direction, that direction. When you are on the top row, you go like this. And then when you are at the bottom, you go this direction. And then on this side, we go up. All right. Now, oh, let me write out all the what's it called? The diagonals. Okay, so the diagonal here along this diagonal was 2, 12, 30. Let me give you a few minutes to think about this one in the meantime. 56, 90, I think you guys said, right? On this diagonal, it was 1, 9, 25, 49, 81, 121, and so on. 9 squared, 11 squared, 13 squared, 169, 15 squared, 225. And then along that diagonal, 0, 4, 16, 4 squared, 6 squared, 36, 8 squared, 64, 100, 144, 196, and then 16, is it 16 square? 256, and so on. All right. Okay, the question is how far the two bugs can be if they are 99 minutes away from each other. What's the closest that they can get? And then hackers guessed it correctly that they can be 1 unit apart from each other. And the critical observation, I don't know if it's gonna ruin the answer, but it's about the number of turns, something that we ignored since the beginning. You can construct a function about number of turns. Based on that number of turns, you can guess what it is. Anyone guessed it so far? So far, I didn't get the correct answer, I think. You can give me the location or the time. No official solution, sorry. Yeah. Yeah, most of the questions, yeah, so I only have answers or very, very brief descriptions of the strategy, but yeah, I don't have long solutions, sorry for that. All right. It turns out, okay, so yeah, this one was annoying. Today I worked a little bit to get to that one. Let me see, where's my notes? Okay, I lost my notes again. Oh, yeah. Okay, yes. Yeah, it's kind of, the answer is based on, okay, so some of you guys are very close to the answer. Okay, so it's annoying. Yeah, I admit it is, it's not easy. But okay, so it turns out the following. If you go up, all right, let me give you the answer first, and then let me tell you where the answer came from. So if my calculations are correct, there will be a corner upright, which will be a 650. And then there will be the next guy, which is 651. And then the one below that would be 552. And then that's pretty much it. These two are separated by a distance of 99. Do you guys see that? Oops, I messed up. Okay, hold on. Bag Academy, yes. These 2 points are 1 unit apart from each other. And yeah, that's it. Well, yeah, these are the times. So what is the exact locations? I don't know. Can you guys tell me what it is? Okay, so I need to figure out the pattern again. So this one was 1 times 2, 2 times 3, and so on. So what are the 2 consecutive integers which give 650? All right, so let me give you the answer. Why is it like this? There's many of them. This is the smallest one. So it turns out the trick is the following. After you make your nth turn, well, the nth left turn, so it's important. So you have to be, all the answers are along this diagonal in such a way, all right? So after you make your nth left turn, all you check is 2n minus 1 minutes before that. Okay, so that sucks. So for instance, well, so 650 is which turn? Okay, so we need to count. Yeah, that sucks. So if you start counting, so this is the first turn, second turn, 3, 4, 5, sorry, second, 3, 4, 5, 6 turn. Okay, let me write the turns now. So this is the second turn. This is yet another parameter. So second turn, 6th turn, 10th turn, and so on. This is the 14th turn, the 18th turn. So you just figure out which turn this guy is. And I think it is, oh yeah, you're right. This is 26 square is, yes, you're right. So this corner over here, this one is 26 square, the 676 on that corner, along that row. So yeah, you can double check. So because this is 26 square, yeah. So you guys do the fun part to trying to figure everything. All right. So, but I did draw a lot of pictures, and I highly recommend you guys also draw a lot of pictures. But the key idea is whatever is the number of turns that this corner is, but it has to be a left turn corner, like it has to be along this diagonal. Then all you do is, if it is the nth turn, you go in time 2n minus 1 minutes. And I think because this is the 50th turn, that's why it worked exactly the way we wanted, because we wanted it to be 99 apart from each other. Here for this question, what is the answer now? What if the 2 bugs are 100 units apart from each other? Okay, so yeah, the previous question, they say it was the 101st turn. Yeah, it might be. So therefore you would subtract 2 times 101 minus 1 from that number to get, wait, no, I think it was the 18. Yes, this one was 25 times 26. So which term is it though? I need the turn number. So the turn number are these numbers. So 2, 6, 10, 14, 18, and so on. What's the pattern for the turns? I don't know the pattern for the turns. Yes, the answer to this question is root 2 is the best thing you can do. But because again, the question says the smallest possible, this one is tricky because, yeah, but anyhow, so, well, actually the answer is staring in your face. It's along that same, okay, let me give you a hint. It's somewhere along here. 100, that's a special number. Which two locations are 100 apart from each other? No, not 552 and 652. Oh, wait, it is actually. That's right, 552 and 652. Oh shoot, I was thinking of this corner. Remember the corner before that would be 24 square, right? 24 square is 576. I was thinking the answer should be this distance in that corner, right? Well, which is apparently not. Your answer is better than my answer. Yeah, I checked the official answer key and it says your answer is the correct one, not 556. No, not 576. It is really 552 is the smallest one. Yes, 552 is the smallest one. Then you keep adding them. So all of them are acceptable, right? Let me do it. So this is acceptable, root 2, root 2, root 2, root 2, root 2, root 2. This is the smallest one is 552, 652. The largest one is 556, 656. I mean, sorry, 576 and 676. That's it. After that, wait, after that it keeps going or? All right, so you guys figure it. Okay. So a couple of other questions. How about this one? F. For how many integer values of t is gt exactly 5 units from the origin? So we want to be exactly 5 units from the origin. How many different ones will be 5 units? So for instance, so we will go like that. Well, I can find 4 of them immediately, right? So the 4 of them would be 1, 2, 3, 4, 5. This one, 1, 2, 3, 4, 5. This one, 1, 2, 3, 4, 5. This one, 1, 2, 3, 4, 5. The bug will definitely crawl through those 5. What else can it be? Can you give me another vertex that it passes through which satisfies this? So you guys keep saying it is 12 of them. I don't think there's 12, is it? Maybe you might be right. Oh, the 3, 4 business. Yes. 1, 2, 3, 4. 1, 2, 3. Yes, that's correct. There's 12 of them. And then 4, 3. 1, 2, 3. 1, 2, 3, 4. This one. And then I see what you guys are saying. 1, 2, 3. 1, 2, 3, 4. This one. And then this one, I guess. So this was 5, 4. And then I need a 3. I think this one or this one. Yes. And then finally, this is a 5. That's a 4, which means, is it? Wait, 1, 2, 3, 4. For this one, wait, this is 4, 4. No, 4, 3 I need, or 3, 4. 1, 2, 3, 4. 1, 2, 3. Over here, I think. I might be wrong. Okay, it seems like that. So these are the 12 points. Now, the question says, okay, so far this answer 12 is correct. If we drop the integer requirement and assume that the bug travels at a uniform rate, how many times is it exactly 5 units from the origin? Okay, so this question is weird. Find the largest and smallest integer t for which gt is 5 units from the origin. All right, so which one is the largest t and which one is the smallest t? Let's just do for the integers. What is the smallest t? Smallest, and then the largest t. This is tricky. Email address is for, thank you again for your email. All right, so what is the smallest t and what is the, t is the time, right? Give me the time. Give me the time when for the first time it reaches 5. the smallest t. If you crawl along this, let's crawl along. When will be the first time we hit one of them? This monster over here, what is it? Yes, that's a 49. And what is the last time we hit somebody? And what is the time for that? The last time we hit is this one. So yeah, be careful. The last time we hit someone would be, well, this guy is at time 49. Yes. All right, at least one person got it. The last time would be this guy. What is the time for that guy? No, not 110. Not 94. 115. Yes, we have at least two people. Ethan and Kartik got it. 115. That's it. The question is asking the distance, the difference between those two numbers. All right, so 115 here. All right, so here's another question. Now, suppose another bug leaves the origin exactly 7 minutes later and follows the same path at the same rate. At what time are the bugs first exactly 5 units apart? Holy. Yes, another bug leaves it, and then at what time are they exactly 5 units apart? And then within the first 30 minutes, how many times will they be exactly 5 units apart from each other? So you guys can see that this doesn't have any end. The questions get harder and harder. Okay, because we are running out of time, let me write down the answer to this question. I think the first time it will be at time 9 and 16. So if you check G9 and G16, I think G9 is 2 minus 1, and G16 is minus 2, 2. And if you check the distance between the Euclidean distance between these 2 points by pi tag, constructing a right triangle, the distance is 5 units. But interestingly, the exact times where this thing will happen again are the following. T equals, so this one was the answer to the previous question. So this one is T equals 8 times in total. T equals 16, that one. T equals, let me write out everything. 19, 20, 23, 24, 26, 28, and 29. Okay, okay, because it's 3 p.m., I don't want to be late like last week. Let me show you a couple of different ways you can change this question, and then I'll blow your mind with something extremely nice. What if we were trying to hit all the positive coordinates, walking like a bug like that? Do you guys see? All I'm doing is x and y coordinates positive. I'm trying to hit all the lattice points like that. And then there's a bunch of questions. Where are you 2008 minutes later? What time do you reach the point 1999? Here, both the x and y coordinates, they are both positive now, right? So this is the point 0, 0. You start at 0, 0, you make up, right? And then afterwards, you try to cover everything. You want to make sure none of the lattice points are empty. All right, that was a nice question. Okay, here's another question. Okay, this question is, if you want to take a screenshot, well, the video is available on our YouTube channel. You can check that. This one, the answer, let me write down the answer. The answer there are to this one is, let me tell you what it is, 384. If you decide to solve it, it's 384. And you can see it on your screen. That's a fun question, a lot of fun. Okay, so how about this? The bug keeps, again, tries to trace everything, except it does these diagonal moves. Yep, that is like, things can get worse. If you are thinking things can't get worse, if you are reading the Dogman book, things get worse, you know. then you need to find a new pattern. Especially you need to find a pattern along the kinks, right? Kink. This is the critical thing. Where are you 2008 minutes later? What time do you reach this point? And things like that. All right, hold on. Now, finally, okay, this is the highlight. And then this is an open-ended question. So here is all the numbers, right? Which numbers I'm particularly interested in? Okay, and then I'll finish with this question. Think of number theory. In number theory, which numbers are the most important numbers? Again, the same pattern. Which numbers? Come on. The primes, right? The primes. The prime. Circle the primes. And what? What do I do after that? and then get rid of all the other numbers, and then do it thousands of times with a computer program. That's what you get. This is called Ulam spiral. Tell me what you see. So each of these dots represent a prime number, and we started at the origin, which is somewhere here. It's pretty cool picture, right? Do you guys see that the prime numbers happen to be along diagonals like that, like the ones which appear frequently? Do you guys see that? And then I can see a lot of primes along this diagonal, a lot of primes along this diagonal, and so on. So there's a 90-degree angle here. Now guess what? So you can search it on Wikipedia, Ulam spiral. That's where I got the picture. Now the critical thing, what if you did spiraling along a, you put like along a, what do you call it? Like a cone shape. And you do the same picture. You try to cover all the points, lattice points across time. And then again, look at the prime numbers. What would be these diagonals? Here we see 90-degree angles. Over there, you know who invented this problem? I learned it today when I was reading the Wikipedia article. Have you been to the San Diego Zoo before? Yeah, if you've been to San Diego Zoo, and I've been there 2 times, I love that zoo. It's amazing. The guy who categorized all the reptiles, he's a monster. He actually, while he was categorizing the reptiles, he was like thinking about some math problems along the same time. So, but yeah, he's the one who figured that the angle is 60 degrees. If you check the angles of where the primes appear, I think they appear at a 60-degree angle most of the time. And yeah, the guy is the highest, well, he's dead by now, but you can also read it from Wikipedia. Pretty good stuff. Okay, so we are over time. Sorry for being a little bit over time. Let me stop the recording. I don't want to lose this session. So thank you guys so much for joining today. So remember, the bug crawls. Don't stop. There's a lot of different configurations. And if you want to watch this lecture again, you can check our YouTube channel as well. All right. So I'll be seeing you guys next, well, on Thursday, I will be back with you guys. All right. Take care.